Welcome back to the series, everybody. Today we are going to cover the video circuit of Cerberus 2100 in a fair bit of detail, but before we get to that, let me just share with you some news. I made a modification and look, it has many colors now, not only 2 colors, now there are 7 foreground colors and black is always the background color. Now this change was done without any modification to the board. It can be implemented in any existing board. The design files, the manufacturing files didn't change. It's only an update to one of the custom chips, which is a programmable CPLD. That's all there is to it. So now specific graphics characters have specific colors. You see different characters on the top have different colors, and across the character set that remains consistent. So this is not a screen color map like for the ZX Spectrum in which different screen positions were associated with specific colors. No, here we have specific character codes being associated with specific colors, so you will never have color clash like the ZX Spectrum had. A character will maintain its foreground color wherever it moves in the screen, wherever it is located on the screen. Now, this didn't break the modularity of Cerberus. That's important. The 3 domains are still compartmentalized and asynchronous. You have the video circuit, you have the computer proper, and the expansion circuit. They remain asynchronous and compartmentalized. No compatibility is broken with firmware or even software, as I'm going to show you shortly. And in fact, this is something I had already prepared the PCB itself to do. I had put those lines there already. I'm using 8 of the 12 spare lines I had put in there. I knew that it could be done. I was just maybe naively hoping that somebody would invest the time and figure out how to do it by themselves. But now that Olimax is going to sell Cerberus, I thought there is no point in waiting for that. Otherwise, people would think Cerberus is condemned to only 2 screen colors forever, and that's not the case. So I made this modification that I had already thought about in advance. So now we have the colors, and it's compatible still. If I load this little game that Alexander Sharikhin wrote when there were only 2 colors on the screen, and he wrote it very quickly live on YouTube even. If I run this game now as it was, you see it still works, and now it has colors. Your anti-aircraft truck on the bottom is blue, the missiles are cyan, and the aircraft is yellow. And this is just out of the box exactly how this game had been written originally. So yeah, this is just to let everybody know that this can be done with Cerberus. I was hoping somebody else would go through the nice puzzle exercise of how to do this. The previous version of the manual actually gave all kinds of hints about how to do that, but I've done it myself. And here is the result. If I wrote this little program poking different characters on the screen, and we can see the effect of all the colors simultaneously on the screen. My capture device blurs it a little bit. I find that it's actually better to capture this by photographing my monitor. But anyway, this is what you have. Alexander had redefined some of the characters in his basic interpreter. That's why there is a difference there. And there is me playing a little bit of defense. So yeah, part of the original intent of Cerberus was to provide this as an exercise for students who would be using Cerberus, to stimulate them to figure out how to put more colors on the screen. The board was already prepared for it. Now I sort of spoiled that by doing it, but I thought for the benefit of Olimax, it would be unfair to keep this machine out as if it only had 2 screen colors. I mean, while I know that it can do 8. Anyway, that's the reason I did this. And now I'll take the opportunity to review the entire video circuit with you, not only this modification, but how the entire thing works, including the guts, the internals of both custom chips, FatCavia and FatSkunk, which form the video circuit, which again is compartmentalized and asynchronous. You can modify the computer proper and the extension circuit or the extension boards without touching this, or you can modify this without touching the computer proper or the extension boards. From this point on, you can follow along everything I'm about to say based on documentation on my GitHub page. I am the byte attic on GitHub. This is the Cerberus 2100 repository. If you go there, there are a number of folders, but there is an explanation here in the README what each folder contains. Right now, we will start by looking at only 2 pages from the Cerberus 2100 hardware manual, which is a PDF file. You can click on it and there will be a preview that will open. Usually it's best if you just click here on download the raw file. It will be faster and you keep a local copy, but you can also wait for the preview. There you go. That's the hardware manual. And I'll be using pages 13 and 14 right now, I believe. The documentation of Cerberus 2100 is pretty complete. I wrote down everything that I myself knew about it. So we will be using here page 13 at first, and then we will go into more details in page 14. Later on, we'll be looking at the CPLD design files, which are here in the CPLD files directory. And we will be looking at fatcavia.pld. This is basically the hardware description of the 2 custom chips, fatcavia and fatskunk, both implemented on CPLDs. A lot of commentary here. So the PLD file is itself its own documentation. And I will discuss with you the syntax of all this stuff. This is basically a schematic written down as opposed to drawn. And when you write it down, it's a lot easier than if you draw all of this complexity here. But we will start with the manual first. All right, in Cerberus 2100, the screen is memory mapped. So every position on the screen, for instance, the first character here on the top left corner, each one of these positions corresponds to an address in video memory. In this case here, this is address in hexadecimal F800. That's the first character on the screen from top to bottom, left to right. The character next to that is at address F801 and so on, until the last character in this row of characters is at address F827. And then at F828 we begin a new row of characters or a new line of characters, and so on and so forth, until video memory address FCAF contains the last character on the screen, which is the one on the bottom right corner. Now each of these addresses, which I'm representing here again linearly and not in a matrix, because in memory it's just a line of addresses. It's all linear. So let's take address F800, which corresponds here to the top left corner of the screen. Within this address there is stored a character code which will point to a position in character memory. That position in character memory will have the first byte of the character that is occupying this screen position, given by this address in video memory. The address after that in character memory will have the second byte of that character, after that the third byte, and so on and so forth, until we get to byte number 8. So all of these addresses here contain the bitmap of the character present in this address, in this position on the screen. Now why 8 bytes? Well, we can see it here. Each character bitmap has 8 lines of 8 bits each. Each bit can be a 0 or a 1. When it's a 1, it means that that corresponding pixel is filled or lit, like here as well, and so on and so forth. And when it's 0, it's because that pixel is unlit or off. So if you look at the position of the 1s and 0s here, you will see that this corresponds to the letter O, non-capital O. Here you go. So you have 8 lines of bits, in other words, 8 bytes until byte 8. Each one of these lines here will be stored in a given address in character memory, and we need 8 of those addresses to complete the bitmap. And all 8 of them are indicated from an address in video memory, which corresponds to a given screen position. That address then contains a character code that points to the first byte in the bitmap. This is in video memory, and this is in character memory. Of course, the next address in video memory, say here, contains another character code, which may point to another position in character memory, where we will find the first byte of the other bitmap, and then all the way to the 8th byte of that other bitmap. And then this position here in video memory, maybe it's pointing to someplace here in character memory. And maybe this one here is pointing to someplace down here, and this one someplace over here, and so on and so forth. But that's how it works. We have 40 columns and 30 rows on the screen. So that's 1200 screen positions, meaning that the video memory has to be at least 1200 bytes wide. It's 2K bytes. In other words, 2048 bytes. The character memory is 2K as well, and that fits 256 character bitmaps. Now, when we print the screen, when we print a frame on the screen, we don't go one character at a time. That's not how it works, because for the VGA standard, VGA knows nothing about characters. It only knows about screen lines. So here you have the first line on the screen, which will correspond to the top byte of the respective characters. So this is the top byte of the character in this position. This is the top byte of the character in the next position, and the top byte of the third character, and so on and so forth. In other words, this byte here of the corresponding character bitmaps. What we have to do is to print the top byte of all the characters here on the top line, and then come back to the beginning of this line and print the second byte of the bitmaps of the respective characters, and then go back once again and do the third until we print the 8th byte of the respective character, until we get to this line here of all the corresponding bitmaps. That's how the screen has to be printed. And only after that we go back to the first byte of the characters in the second row of characters, and then the second byte of the characters in the second row of characters, the third, the fourth, the fifth, the sixth, the seventh, and the 8th byte of the second row, all the while coming back. And only we've printed all 8 of them, now we come back here, one more position down, and we do this until we print the last byte of the last character of the last row of characters. That's the idea. So we have to have several counters to do this. Now, to complicate it a little bit more, you would think, well, we have to return to a single row of characters 8 times because each character has 8 bytes. But I'm going to double sample each of these rows in order to fill the screen while keeping the resolution within limits, because dual-ported memories are very expensive. So I'm going to return not 8 times, but 16 times. So we will print the first row of all the characters on the first line. Then we will return and print that first row again, just underneath. So we print the first row twice. This first byte here will be printed twice. Once, and then a copy of itself underneath. And then we go to the second row and print it once, return and print it twice, and so on and so forth, until we have done this 16 times, 2 passes for each of the 8 bytes in each character bitmap. We will also double sample it horizontally. I'm showing you vertical double sampling by a factor of 2. Later on, I will explain that we will also double sample horizontally. So each Cerberus 2100 pixel becomes 4 screen pixels. So it's doubled in length and doubled in height, 4 times the area. So we need a lot less video memory to store all the characters on the screen. I'm using a fairly high-res VGA mode for this. That's the reason. All right, so how do we do all this? This is the circuit. It uses 2 custom chips, Fat Cavia and Fat Skunk. Fat, it's because these are more robust, bigger versions, more pins than the original Cavia and Skunk in the original Cerberus 2080 a few years ago. The first one, both of them are implemented in complex programmable logic devices, CPLDs. The first one, Fat Cavia, is responsible for continuously scanning the video memory and the characters in the character memory that correspond to the character codes that are read out from video memory. So it has a number of counters inside to produce the addresses that address the video memory. Remember, it has to come back to the same row of characters 16 times to double sample it and print all the bytes of the character bitmap, and then it goes to the next row. So there are a lot of counters here to keep track, to manage the proper jumps, the proper counting. Then a character code byte will be read out from video memory here, character code, and that will become the most significant 8 bits of an address for the character memory. These 8 bits identify the character we are trying to print. But remember, if we go back to the previous slide, each character has 8 bytes, not only 1. And with the character code, we are pointing only to the memory position of the first byte of the character bitmap, but there are another 7 of them. So we need another counter that counts from 1 to 8 or 0 to 7. So we need 3 bits for that counter. No, 0 to 7, you need 3 bits. And those are the 3 bits here. They are also produced by Fat Cavia by another internal counter. So not only we know which character we are trying to read out from character memory, we also know which byte of the corresponding character bitmap. Together, 8 plus 3, we have the 11 bits that we need for a memory that is 2 kilobytes big. So that's how the address is formed. So once we know which character and which row of the character bitmap, we read out that row, which is 1 byte, and we store it in an internal shift register within Fat Skunk. And from here, we can shift the corresponding bits out to the VGA screen, to the monitor, through the pixel clock. So here you can see that the pixel clock has to be at least 8 times faster than the Cavia clock, because Cavia is reading out 1 byte at a time from the character memory, but then we have to shift out all the 8 bits of that byte before we can load another byte from character memory. So the pixel clock here has to be at least 8 times the speed compared to the speed that Cavia is reading out bytes from character memory. I'll come back to this in a moment. All right, what else do we need to do? Well, we have color processing. How do we decide with which color to print the ones here in the shift register? Suppose this is 0, 0, 1, 0, 0. When you're spitting out a 0, well, that's the background color. It's black in all cases. But when you're spitting out a 1, we need to know which color to use. And we will know that because the character code byte that Kavya reads out from video memory goes not only into forming an address for character memory, it's passed along to FetSkunk here, and then internally it's routed to color processing. So every time there is a 1 coming out of the shift register, this logic here will check, okay, which character code does that 1 correspond to? And then it decides with which color to print it to the screen via the RGB signals. That's the idea. So what you have here is not a color map. We are not deciding the color based on the screen position. We are deciding the color based on which character we are going to print. A character code, a number between 0 and 255. And we don't have any color clash because that color will follow the character wherever that character moves on the screen. The color follows it because it's character dependent and not screen position dependent. Now, in addition to this, FetSkunk also has counters to know when to produce the sync pulses, the horizontal sync pulse and the vertical sync pulse. In doing that, it knows when it is in the blanking interval, and then the RGB lines go to 0 during the blanking interval and the sync pulses are produced. During the blanking interval, FetSkunk will withdraw the chip enable signal that goes here into the two memories, the video and the character memory. Now remember, these are dual ported memories, so the computer proper is here on the other side accessing the same memory, both video and character memory. And because the computer proper, which is here, can also access character memory on the fly, all the characters are redefinable on the fly. So you have at least 4 characters for each color, but you can define them to be whatever you want. The computer can define them in software to be whatever the program wants. Now, when we are in the blanking interval here, it's good to disable this side to the right of the memories. It's good to disable this side because that avoids conflicts with the other side. When this side is disabled, the left side is still enabled, so the computer proper can access memory. And because the right side will be disabled, there will be no pauses issued when the same address is being accessed from both sides. No address will be accessed from the right side because this right side is chip disabled. So it speeds things up a little bit. That's the purpose of this signal produced by FetSkunk, because it is FetSkunk that has the counters that know when we are in the blanking interval. All right, now the pixel clock is 25.175 megahertz. But remember, we want to double sample each of these bits to fill the screen using less video memory. So what we would do is the shift register clock with which we clock the shifts to the right here, the shift register clock will be half of the pixel clock. By making it half the pixel clock, each of these bits here will be sampled twice, tick, tick, and then it will shift, and then 2 ticks again, tick, tick, and then the next one, and so on and so forth. Now remember that the Kavya clock has to be 8 times slower than the shift register clock. That's critical because you need 8 cycles to shift it before you can reload it. So the Kavya clock is 1/16 of the pixel clock. That's the reason why it is 1/16 of the pixel clock. It has to be 1/8 of whatever this is, and this is half in order to double sample. And as we've seen before, here, each line corresponding here to the top byte of each character bitmap on that row of characters will be scanned twice. You will get to the end, come back, and scan it twice, and then print the next row of bytes of the respective character bitmaps, get to the end, and return, and only then go back to the third, and so on and so forth. So we make the characters twice as tall, and by sampling the shifter register twice, we make it twice as large, and therefore we preserve the aspect ratio. That's the idea. I think that covers it. We can go now into the actual code for the two custom chips, FAT-Cavia and FAT-Skunk, to look into more details. Okay, let's look more carefully now into FAT-Cavia. This is in the repository and in the CPLD underscore files folder. And this file is the fatcavia.pld. So this is the hardware specification of the logic within FAT-Cavia, which is the chip responsible for scanning video memory and character memory. I'm not going to explain every single gate. There are many things you can look up online, like how you build a counter using toggle flip-flops. I'm not going to explain how that logic is built. I'm just going to show you this is the lines in which a counter made with toggle flip-flops is specified. Otherwise the video will be too long and I will be just doing, repeating stuff that you can find online in free digital electronics lessons, Boolean logic, stuff like this. I'm just going to give you some indications of how to read the notation of this language called couple, which is the CPLD design file language used by Microchip and the former Atmel, which is now part of Microchip. So the first lines just specify what this file is, file name, date, author, etc. These are just some directives for the compiler. I'm not going to go into the details of what this is. To some extent, this stuff is intuitive. Pre-assigned keep, it just means that I'm telling the compiler, keep the pin assignments that I chose. Don't invent anything else. Keep it as I did it. These are all commentary. Stuff that starts like this and ends like this. These are just comments, and it's part of the documentation of this file. Now here, the declaration of the input pins begin. So this is the Cavia reset that comes from Skunk. This is the Cavia clock that comes from Skunk. These pins here are the output of video memory. The output of video memory is a character code, which becomes part of the character address. So I'm calling them character address 0, character address 1, until character address 7. These are the most significant bits of the address for the character memory. The least 3 significant bits are a separate counter that I'm going to show. These pins here, they are used in the PCB. There are traces connecting these pins in Cavia to other pins in Skunk, but this configuration file is not using them. Now the output pins are declared. This is basically the 11 bits of video memory address from VMA, video memory address 10, down to video memory address 0. Then we need the same thing for the character memory, 11 bits. So character memory address 0, 1, 2, 3, blah, blah, until character memory address 10. So these are the outputs. Now pins that can work as inputs and outputs. These are the pins that I put on the PCB, but I didn't use in the original version of this file. I am using 8 of them now, as I'm going to show. These pins here are routed to and from Skunk, so they connect FAT-Cavia to FAT-Skunk. Now buried states are basically the declarations of the internal flip-flops, memory elements, and you don't need to assign them to pins, even though they are located in the neighborhood of specific pins. I want to let the compiler be free to decide which of the physically available flip-flops to use. I'm just telling the compiler I will need these many flip-flops and I'll call them this. So in the first case here, LPC is what I call the token line passes counter. A token line is a character line or a character row on the screen. There are 30 of them, each one having 40 columns or 40 characters. I'm calling them a token line here for historical reasons. That's how I wrote it down in the original Cerberus 2080. And this is a passes counter. Remember, we have to go over each token line 16 times. Why? Because there are 8 bytes per character, and we need to double sample each of them. So 8 times 2, 16. So we need a counter with 4 bits, LPC 3 down to LPC 0. Because, yeah, that's how you count to 15, 0 to 15. In other words, you count the 16 passes we need to do over each token line. So this is the passes counter. Now, the same thing for TLC, but now 6 bits. That's the token line counter. So not the passes counter. Here I'm counting the tokens or the characters in the line. And there are 40 of them. So I need 6 bits to do that. It's actually 0 to 39 to count to 40. I should change this. But now everybody will understand what is meant here. Now this is the fallback address. And the reason is the following. Remember, we have to pass over each token line 16 times. When we get to the end of a pass, we have to know the starting address of that token line, so we can go back to the beginning. There are 30 lines, so at each time you need to know what is the beginning of the line you have to come back to. I'll call that the fallback address, which is basically the address of the first token in the line, the beginning of the line. And I will store that address in these 8 flip-flops. The fallback address 10 to fallback address 3. Now, why do I need only 8? Because in principle the address is 11 bits wide. Well, it's because I know these are always the first address in the line. In other words, they are multiples of 40. And therefore the 3 least significant bits are always 0. So I don't need a flip-flop to store that. I know that they are always the same. Anyway, that's why I'm only declaring 8. But I call them FBA 10 down to FBA 3 in order to remind myself and remind you, if you're studying this file, that there are another 3 least significant bits that just happen to be fixed because these are all multiples of 40. Now comes the actual logic declaration. First, we assign the values to the pins that correspond to the character memory address. Remember, 11 bits. So, as we discussed earlier in this video, the 8 most significant bits, which I call the character address, are basically the character identifier. It's a byte that tells me which character it is. But I also need to know which byte of the 8 bytes constituting the character's bitmap I'm addressing right now. So I need another 3 bits. And I explained it to you already in the circuit diagram. You see them back here. These bits are spat out from video memory identifying the character. Now I'm going to use some of the previously free lines to pass the character address on to Skunk as well. So I'm using it to address the character memory, but I'm also letting Skunk know which character identifier we are dealing with, so Skunk can choose the correct color for it. I'm going to show Skunk later on in this video. Now, this is the token line counter. We looked at it during the declaration. Where was it? Oh, it was in the buried state. Yeah, this is the token line counter, 0 to 40, and the LPC was the token line passes counter, 0 to 16, or 0 to 15, 1 to 16. So these are the bits used here. It's the passes counter that tell you which byte of the bitmap address you are on. Now this is the actual implementation of the counter. Up above, I just declared it. Now I'm actually implementing it. I'm using toggle flip-flops to implement each of these state holding elements in the counter, and these are flip-flops. And I'm using toggle flip-flops. You can build a counter using toggle flip-flops. I'm not going to explain to you in this video why it is like this. It's much easier to explain this with a diagram, which I don't want to do. But if you go online and you Google binary counter based on toggle flip-flops, you understand why it is like this. So the .t is the input to each flip-flop. .ck is the clock input to each flip-flop. Because it's the same input for all of them, I'm specifying all of them together. TLC5 down to TLC1 .clock, they are all the same. It's the caveat clock that comes from Skunk. This is the asynchronous reset, which is the same for all the 6 state holding elements, all the 6 flip-flops, and they are the caveat reset, which comes from Skunk. Or a hash is a logical OR. So the flip-flops are asynchronously reset either when a caveat reset comes from Skunk or when the token line counter reaches a certain value. What value is that? Well, it's when it gets to 40. That's the end of the line, so you should reset the counter, go back to 0. This is what this is saying. The synchronous reset can be forced from the outside by Skunk, by pulling this line, or it happens automatically when you get to the end of the counting. You should go back to the beginning, because that's going over that token line again, one of the 16 passes we have to do on each token line. Then here, this is the token line passes counter. So this one counts to 40, 1 to 40, or 0 to 39, which is the number of characters on a line. And this counts the number of passes that you do on each line. You have to do 16 passes. So again, I am using toggle flip-flops in this configuration, which is basically a counter. The clock for everybody is the same. It's the caveat clock again that comes from Skunk. The reset is the same. It comes from Skunk. But now I'm using a clock enable term. In other words, this counter only clocks when this condition holds. And what is this condition? Well, if you look at the logic here, TLC5 needs to be 1. The % is a logical AND. So TLC5 needs to be 1, and TLC4 needs to be 0, because the exclamation mark is an inverter. So this has to be 1, this has to be 0, and this has to be 0, and this has to be 1, and this has to be 1, and this has to be 1. Well, what does that mean, this combination of 1, 0, 0, 1, 1, 1? Well, that's when you get to the end, that's 39. So only when you get to the end of the token line, the end of the row of characters, is the clock enabled and the line passes countable clock. In other words, you only count another pass when you actually passed the entire line, when you got to the end of the line, which happens when the token line counter reaches 39. So you tick on this counter, and you would tick 16 times, and then you go to the next token line. That's the idea. Now, why is the reset here only caveat reset and doesn't have a condition like above? Well, it's explained here. This counts from 0 to 15 because it only has 4 bits. So when you get to 15, you don't need an explicit reset. You just let it run and it will go back to 0 by itself. Unlike here, because here you're counting to 40 or 0 to 39. So you could count further to 41, 42, because you have enough bits in the counter for that, but you don't want to. So you have to explicitly reset at the moment you want it to reset. Here you don't need to do that. You don't need to do that because it will go back to 0 automatically, unless you get an external reset from Skunk, because Skunk has decided that it has reached the end of the frame or needs to resynchronize, and then it resets caveat. Now, this is the video memory address counter. So what have we counted so far? We've counted the token line. Each token line has 40 characters, so we have to count to 40. We have to pass over each token line 16 times, so we have to count to 16. But we also have to increment the video memory address in order to scan the video memory. So we need yet another counter, this one with 11 bits, because we are counting to 1200. There are 40 times 30 characters, in other words, 1200 characters. So we need to count from 0 to 1199 for each frame. Now we start with this term here, a load term, which is basically, it checks if we have done all the 16 passes in a token line. In other words, when TLC5 and not TLC4 and not TLC3 and TLC2 and TLC1 and TLC0. So that's the address we need to reach. That will mark the end of the token line. And the line passes counter cannot have reached the end. This is an inversion. And here you're ending the positives. So this will be true when all of them are 1. And when all of them are 1 and this is true, the result will be 0 because it's negated. What this means is that for as long as we haven't done all the 16 passes yet, we should go back to the beginning of the line. We should fall back to the initial address and do another pass. That's what it means. This load is 1 when we have to do another pass over a character line or a token line. And this is the video memory address counter, which is again implemented with toggle flip-flops. And the logic here means if we have to go back, then LD is 1, and then you wire things this way for the address line 10. And when you don't have to fall back, then you want to count through, then this is how the wiring happens. Now, why it is like this, I will let you figure out by yourself after you have Googled binary counter with toggle flip-flops, and then you understand when I want to do a load, return to the initial address, and when I want to count through, and why the logic is like this. And of course, the clock for all of these 11 flip-flops is the caveat clock. The reset is the synchronous reset that can come from skunk, or you have to reset when you get to the end of the frame. In other words, when you get to 1200. And if you look at this, VMA 10 has to be 1, and VMA 0 has to be 0, and VMA 8 has to be 0. And if you look at the ones and zeros that you get here, you see that that's the end of the screen. You got to the bottom right of the screen, so you have to go back to the beginning, so you have to reset this counter. Now, there is a term here that you've seen before, fallback address. So sometimes you just use the video memory address line, but sometimes you use the fallback address. In other words, that's when instead of counting through, you want to go back to the beginning of the token line. So who knows what the beginning of the token line is? It's these lines here, fallback address. You see them in every term. Fallback address 10, fallback address 9, fallback address 8, 7, and so on and so forth. So where is the logic that determines what the fallback address is? It's right here, which is the last part of caveat. The fallback address is stored in a set of flip-flops. In this case, they are D flip-flops, which are the most common flip-flops. You know, D flip-flops is the archetypal flip-flop. The .D means the input, the data input to the D flip-flop. So the fallback address 10 flip-flop will be wired to video memory address 10. Fallback address 9 flip-flop will be wired to video memory address 9, and so on and so forth. In other words, when these flip-flops are clocked, they will store the value in these address lines here. Flip-flop 9, when it's clocked, will latch the value of video memory address 9. Flip-flop 8, when clocked, will latch the value of video memory address 8. So you're basically latching a video memory address. The question is, when do you latch it? Well, you latch it in the beginning of each line, right? That's the fallback address. The fallback address is the beginning of each line, because that's what you have to go back to when you finish scanning the line. All right. And what is then, how do you know what moment that is? Well, it's written right here. It latches once per token line at the start of the first pass. In other words, when the counters are 0, you know, there is an inversion here in front of each line of each counter, such that the compound result of this large logical AND will only be 1 when all the counters are 0. At that moment, the fallback address flip-flops will latch the video memory address, whatever it is. And then when you get to the end of the pass, it will load the fallback address according to this logic, which means that the counter will go to the beginning of the token line again until it has completed 16 passes. That's the idea. I trust it's not too complex. Let's get to skunk now, which is even simpler than this. All right, here we are with the FAT skunk PLD, the second custom chip in the video circuitry. It's still within the CPLD _ files directory of the Cerberus 2100 GitHub under the ByteAttic account. Like for Kavia, FatSkunk starts with some preliminaries, just the name of the file, which device it applies to, who did it, at what time, and so on. I added this commentary here to say that this is the multicolored version of Skunk, so people don't confuse it with the original one. Then we have some compiler directives, a lot of commentary here to give some background. And now we have the pin declarations. First, the inputs. This is the general reset. That's the pixel clock that comes from the oscillator. Now, these are the inputs coming from character memory. Remember, FatCavia is scanning video memory and character memory. And what character memory spits out is 1 byte at a time from the bitmap of a given character. So this is an input to Skunk from the character memory into Skunk. So that's the character byte bit 0, character byte bit 1, until character byte bit 7. So each of these character bytes is 1 out of 8 bytes of a character bitmap. Now I define a field here in which I just swap the order around, and this is just because of the way the shift register is implemented within Skunk. We have to swap the order around, and using the field the field clause in couple is a very easy way to just order it in a mirrored way and solve the problem. Now these are the output pins. The first one is buffer enable. The reason for this is purely electrical. It's not logic at all. These CPLDs cannot get a clock before they are fully powered up. Otherwise, you screw up the contents of all the flip-flops in the CPLD and it will not work. So to prevent it from getting a clock before it's fully powered up, I pass the clock through an external buffer, which must be enabled by this buffer enable signal, which the CPLD, in this case Skunk, can only generate when it's fully powered up. So this ensures that Skunk never gets a clock before it's fully powered up, because it only produces the BE once it's powered up, and the BE controls the buffer that passes the clock to Skunk. Now we have the sync pulses, the horizontal sync pulse and the vertical sync pulse. Each one of them has a dedicated pin, because that's what the VGA connector expects. Then we have the 3 RGB values, red, green, and blue. The Kavia clock is an output, it goes to Kavia. This is the chip enable for the right side of the dual ported memories. This is the Kavia reset, which goes to Kavia. Some free traces that are on the board, and there are pins dedicated to them, but I'm not using them at this point. Then we have the inputs and outputs. The free signals were IOs. You could use them either as inputs to Skunk or outputs to going to Kavia, but now I'm already using them as inputs. These are the Kavya character address 0, Kavya character address 1. In other words, it's the character code, which also forms part of the address for the character memory. That's why I'm calling them Kavya character address. But these are just the 8 bits of the character code, which Skunk needs to know in order to determine which color it should give to active pixels of a certain character's bitmap. Another pin that's still free. And now the buried states, in other words, the flip-flops. Now I have 8 flip-flops dedicated to latching and holding the character address. In other words, the character code that comes from Kavya. And explain why in a moment, but just to give you an idea, once Skunk latches a byte from character memory into its internal shift register, it gives a clock pulse to Kavya, so Kavya can go to the next address. And the reason for that is that we need to overlap this function in order to give the two memories the required access time. So as soon as Skunk latches the output of character memory, it tells Kavya, okay, go to the next address, because I already latched that value. It is safe with me now. But if we need to know the character code that corresponds to what we just latched, we need to latch the character code as well, because the character code is going to be something else as soon as you clock Kavya. Kavya go to the next character code. And we don't want to mix up the next character code with the one we are printing on the screen right now. To avoid that, we need 8 flip-flops or a register to latch the character code coming from Kavya at the right time. Then we have some other signals which have to do with VGA timing. This is one when we are in the front porch. This one is one when we are in the horizontal sync pulse. This is one when we are in the back porch, horizontal. And then the same thing for the vertical part, the vertical front porch detector, vertical sync pulse detector, and the vertical back porch detector. This is just VGA stuff. Now we need a horizontal counter because we are printing the screen now, so we need to know in which pixel in the screen we are. We also need to know in which row in the screen we are. So we need a horizontal counter with 10 bits because it needs to count to 800. The VGA mode I'm using is 600 by 400 pixels. That's what you see on the screen. But of course, we need to keep on counting when we are in the blanking interval to know when we are in the front porch, in the sync pulse, and in the back porch. So we don't count to 600 only, we count to 800 horizontally. And vertically, we count to 525, not only 400, even though we only see 400 on the screen. Now this is the shift register, the most significant bits of the shift register, 7 bits. Of course, we need 8, but the 8th bit, I'm calling it a different name, output bit, because the VGA connector only sees the least significant bit of the shift register. It doesn't see the 7 more significant ones. So it's useful to give it an evocative separate name. Instead of shift register 0, I'm calling it just out bit, because that's the one that goes out to the VGA connector. Now I'm using this field declaration again. It's a way to refer to a number of signals as a whole. So here I'm saying, okay, the shift register signal 7, 6, 4, 5, 3, 2, and 1, plus the out bit, that forms the field shift register. And shift 1 right, I just append a 0 in the place of the most significant bit, and I drop the out bit. This is how we implement the shift. The shift just adds a 0 and drops the least significant part, which is exactly what a shift register does. This is the buffer enable. I'm just saying that it's a binary 1, but this will only be 1 when Skunk is fully powered up, and only then it will get the clock. Now this is the non-blanking. The non-blanking will be true when we are not in the horizontal front porch, when we are not in the horizontal sync pulse, when we are not in the horizontal back porch, not in the vertical front porch, sync pulse, and back porch. When we are in none of these phases, we are printing pixels on the screen. We are not blanking. So this is the not blanking variable. Remember, an exclamation mark is a negation, and an ampersand is a logical AND. Now we need to define the color of the active pixels that we will be printing on the screen, depending on the character value. The first thing we need to do is to latch the character code. So we latch the Cavia character address into a character address flip-flop. And in this case, it's a D flip-flop. So when this flip-flop clocks, it will latch the value coming from Cavia. And now Cavia can change this value because the old one will already be latched and we will know what it was. So the question is, when do we clock it? Well, we have to clock it at the same time that we latch a byte from character memory in the shift register, because they will correspond to one another, the character code and the byte that is in the shift register. We determine the color based on this correspondence. So we have to latch them at the same time, and they are latched at this moment. There is a 4-bit counter internal to Skunk. These are the 4 bits. And when the 3 most significant bits are all 0 and the least significant bit counts to 1, that's when we latch a character in the shift register, a character byte. So that's also when we have to clock these flip-flops to latch the corresponding character code. And the reset is just a global reset. Now we determine the color based on those latched values of the character code or the character address. So these equations are all based on these latched values here in the D flip-flops, which change only at this moment, which is when you latch a byte in the shift register as well. Now, the equations here are such that the out bit has to be 1. In other words, we cannot be printing the background. And when out bit is 1, we are doing a foreground color. So all of this only happens when out bit is 1, when you're dealing with the foreground. When out bit is 0, that's the background, we do nothing, the screen stays black. And the combinations here, all these ANDs and negations, they correspond to a particular character code in our character set. And I decoded here. CA7, 6, and 5, they should always be 0 because the higher character codes, they are all black and white. So these should always be 0. What matters are these 5 values here. And I'm saying what they should be in order for the color to be green. So when CA4 is 0 because it's inverted, that's the 0. CA3 is 1, that's the 1. And CA2, 1, and 0 are 0, these are the zeros. Then the green channel is active, and this is green. The green channel can also be active when it's 0, 1, 0, 1, 1. But then the red channel here is also active. So what you get is a yellow, because in RGB, green plus red is yellow. And that's how you can read all of these equations. Now, when CA5, CA6, or CA7, when any one of them, the hash is a logical OR. When any one of them is 1, then it's white. It's a black and white. These are the higher order characters in the character set. Same thing for the red channel and the blue channel. And when you combine, of course, blue and red, you get purple. And when you combine blue and green, you get cyan or cyan. I don't know how you pronounce that. A very light aquatic blue. All right, now this is the chip enable for dual ported memories. It's active low. So when we are not blanking, in other words, when we are blanking, then this is 1. In other words, it disables the memories. So when we are in the blanking interval, the right side of the right ports of the video and character memories will be disabled, such that the other port, the left port, is always available to the computer proper. Now this is the Cavia reset logic. We want to reset it at the end of the frame, and the frame ends after 525 pixel lines, we are not talking about character lines anymore. It's not token lines anymore. Skunk deals in pixels. So this is at the end of all 525 pixel lines, including the 400 that are visible. The other 125 are part of the blanking interval, but they need to be counted anyway. And only at the end of that, and if you do here, V9 is 1, V8 is 0, V7 is 0, V6 is 0, 0, 0, until V3 is 1, 1, 0, 1. That's 525. That's the number you get. And V is the vertical counter, which I didn't put in this file yet. It's below. So if you're a programmer, you may be confused with this. I am using variables here that I didn't define yet. I declared them, but I didn't define a value. How can I do that? Well, this is not code. This file here is not a temporal, a time-based sequence of instructions to be executed in order. This is not what you're seeing here. What you're seeing here is a wiring diagram, a schematic specified through letters and numbers instead of graphics. But this is not a sequential list of instructions, such that if you change the order in which you say things, then the result changes. No, this is a wiring diagram. So the order in which you make the statements don't matter. What you're saying here is that there is a pin called caveat reset that will be connected, wired, to an internal flip-flop part of a vertical counter in such a way that this flip-flop is not negated, but it's ended with this flip-flop, which in turn is negated. In other words, this is the specification of wiring, not a list of instructions to be executed in time. This is a spatial specification of wiring in space, not in time. That's why I can use things that I'm only going to define down in the file and that aren't defined yet. There is no yet because this is not time, it's space. But you get the point. So these are the values of the vertical counter, and I should reset caveat when this counter counts to 525 because that's the number of lines, pixel lines in this VGA mode. Now that's the clock circuitry. Remember, there were 4 bits in that counter. It's an internal counter that Skunk uses, and again I'm using T flip-flops, and you can look it up online why it's wired this way. The clock for those 4 toggle flip-flops is the pixel clock that comes from the oscillator. There is an asynchronous reset, which is a global reset, comes from the outside. And the count enable is basically the non-blanking. This is exactly the same as the NB that I specified above here. It's exactly the same as the NB. So I could have used NB down here as well, down here. But I don't know why I did this. I just wrote it all out again. The compiler will optimize it. This is just NB. So the count is enabled when we are not blanking, because this counter refers to what is actually visible on the screen. And the caveat clock is given by the second flip-flop. This is a counter, so you can imagine this counting from 0 to it's a 4-bit counter, 0 to 15. So if it's 0, it would be 0, 0, 0, 0. 1 will be 0, 0, 0, 1. And then 2 will be 0, 0, 1, 0, and so on and so forth. If I take S1 as the clock, I will be automatically dividing the pixel clock by 16, which is what caveat should see, as we discussed before. Now, finally, we have the counters. That's the vertical counter here. And again, it's made with 10 toggle flip-flops. It's the pixel clock that goes there. There's a global reset, or when it reaches the end, and the end is the 800th pixel in the pixel line. Again, only 600 are visible, but we need to count to 800 because of the blanking interval. We need to know when we are in the front porch, in the sync pulse, and in the back porch. And if you decode this equation, when the horizontal counter bit 9 is 1 and the horizontal counter bit 8 is 1 and the horizontal counter bit 7 is 0, and you translate all this, that's 800. That's what you get, 800 in binary. Now we have the individual detectors. We need to know when we are in the front porch, when we are in the sync pose, and when we are in the back porch. And it's done just like before. We have a D flip-flop that is the detector. We wire a binary 1 to it, 5 volts, and the clock is given by this. In other words, the output of the flip-flop will only be 1 when this condition is met, because then the clock pulse will latch 1 into the flip-flop, and that will go into the output of the flip-flop. And if you decode the value of the horizontal counter corresponding to this, it's 640, which is the beginning of the horizontal front porch. And again, there is a global reset, or we reset at the end of the front porch, which happens when we count to 656, which is this combination of values in the horizontal counter. So this is it. This is the same thing for the sync pulse detector, except that the values are different. So these equations are different because we are somewhere else in the counting. And the same for the back porch detector, again, except that these equations are different because the counts have to be different. And this is just a variable, that's the horizontal sync pulse. It's just the opposite of the horizontal sync pulse detector, and that has to do with the polarity with which the VGA standard expects the sync pulse to take. So we count in one polarity, but the sync pulse itself is reversed polarity. Again, the exclamation mark is an inverter. And then we do exactly the same thing, but this time with the vertical counter. So only here we are specifying the values of the vertical counter, even though I already used these values here. And we can do that because, again, this is not a list of instructions. This is spatial wiring specification. I'm saying what is connected to what. So this is the horizontal counter. And then we do the same thing for the vertical, this is the vertical counter. And we do the same thing we did for the horizontal one, we do for the vertical front port detector, the vertical sync pulse, and the vertical back port detector. And again, we invert the detector to generate the vertical sync pulse now instead of the horizontal sync pulse as before. And now we get to the shift register, which actually produces the pixels that become the RGB values after they are color processed. And the color processing was here. Was this stuff. That's the color processing. But it's all conditioned on the out bit. So what is the out bit? Well, the out bit comes from the shift register. Because what is the out bit? Well, we are using this field, shift register. And if we go back to how we defined the shift register, all the way at the top. Let's see, where is it? Here. Field shift register is this. So the least significant bit is the out bit. So that's why, if we go back to the bottom, that's why the out bit is actually defined here, even though you see no mention of the out bit here, because it's already entailed by this field definition, here and here, yeah? So the clock to the shift register, dot clock, this will go to all 8 flip-flops, is S0, which is the lowest, the least significant bit of the internal counter. That will basically divide the pixel clock by 2. Because the clock will only happen when S0 goes from 0 to 1, not from 1 to 0, and that alone will halve the pixel clock. So we take at S0, and now we have these equations here. They are short, but they may look complex. I have to take a decision here. I will either be doing this, wiring this into the input of the flip-flops, all 8 of them. They will either be wired to this, or they will be wired to this. And notice that I'm using the same condition on top and at the bottom, but in the bottom it's inverted. So the wiring now is such that either this will be wired to the flip-flops, or this will be wired to the flip-flops, depending on whether this condition is true or false. And this is the OR. So you see, you could draw this as a schematic with inverters, ANDs, and ORs, and you would see that this is a form of conditional multiplexing, in which the control input of the multiplexer is this equation. Now, to explain to you what this means, it's easier if I go back to the manual, to the hardware manual, which is also on GitHub. I already chose the page. It's page 17 here at the bottom. This is the counter we are dealing with. It's a 4-bit counter, counts from 0 to 15. And the most significant bit is S3, the least significant is S0. And as we've seen, S0 is the clock. So when do we get a clock in the shift register? Only when S0 is 1, when it goes from 0 to 1. So this is a clock tick, this is a clock tick, this is a clock tick. When S0 is 0, nothing happens, because the shift register is not being clocked. Now, if you look at the equations, the cavia clock is when S1 is 1. In other words, this is the cavia clock here, this line, when S1 goes from 0 to 1, and everything else is 0, because you see, negated S3, negated S2, S1, and negated S0. So this is the cavia clock, right here. It's 1 out of 16 possible states. That's why the cavia clock is 1/16 of the pixel clock, which is what clocking the counter here. Now let's go further. Let's look at this condition. Negated S3 and negated S2 and negated S1. In other words, S3, S2, and S1 need to be 0. When does that happen? It happens here at the top and here, the first two lines. In all other lines, you don't have all three of them being 0. Now, in this first line, S0 is 0, so there is no clock. Nothing happens. So this condition here only happens here on this line. So on this line, this condition holds S3 is 0, and S2 is 0, and S1 is 0, and we have a clock. Then I will put the char byte mirrored into the shift register. In other words, I'm loading the shift register with a new value coming from character memory. This is what happens at this point, at this cycle here. We load a character into the shift register. And as we've seen, we will also load the character code into another register in order to know which color to attribute to the positive bits in the pixel map, in the bitmap. Now, this inversion here is the parenthetical condition that we saw before. And as we saw before, this condition holds only here. So if I negate this condition here, then in all other cases, this will hold. In other words, on the top line here, the load only happens at this point. And the bottom line, which is a shift 1 to the right. Remember, we put a 0 on the most significant bit and shifted all others 1 position to the right. That will be the wiring in all other cases when you get a clock tick. In other words, this is a shift. And you will shift every time S0 is 1. And if you count it, you will see that we'll be shifting 8 times. It's exactly what we should do. And here, when we've shifted 8 times, here we load another byte into the shift register, and then we shift it 8 times, and then we load another byte and shift it 8 times. That's what you're seeing here, written down with letters and numbers, which is much more succinct than if you draw schematics, but it requires that you know what you're doing just as it does if you were to draw a schematic. In other words, the information in this piece of text is exactly the same information in a schematic in which you are drawing the gates. So you actually have to design everything down to the individual gate and individual flip-flop level, because it's the same level of information. It's just that the form is different. Here we are using text instead of complex schematics which look like noodle soup and you have to follow the wires. Well, here you don't have to follow the wires. Here you just look at the names of the signals and you don't have to draw gates. You just look at the exclamation mark, an ampersand, and a hash for an OR, and an equal for an attribution. In other words, for a connection between two wires. That's what's happening. So there are 16 states. You load, you hit the Cavia clock only once out of 16, and you shift 8 out of 16. That's why you have half the pixel clock to double sample the pixels horizontally, and you have 1/16 of the pixel clock in Cavia to double sample everything horizontally. That's how you get all of that specified in this little bit of text here. Only 3 lines, you see? Super easy, super clear, and in Dutch we say overzichtelijk, amenable to overview. You can figure it out at a glance. You land your eyes on it, and you know what it's doing. See, you have the same condition here and here, ended with something else, and in one case that condition is inverted. Well, that's a multiplexer. You immediately see that. You immediately see which fields, which lines you're using from the counter. Much easier. And then we are left only with the reset, which is either the general reset or this condition based on the lines of the horizontal counter. And if you decode what binary value this means, this is at the end of each frame line. When you get to the end of the frame, you're going to start the horizontal blanking interval, then you reset everything. You reset the shift register, because in the VGA standard, you should not put out RGB values during the blank interval. The RGB values should be grounded during the blanking interval. Otherwise, you get electrical issues, as I experienced myself. To prevent that, we just reset asynchronous.ar is the synchronous reset input of the shift register. We pull that line down, we reset it when we are in the blanking interval to avoid electrical problems. And this is it. You've seen everything now. It's the whole of the video circuit of Cerberus 2100 specified down to the individual gate and flip-flop in a manner that is very amenable to overview, very easy, but still with all the information in there. You see everything. Nothing is synthesized, nothing is automated, everything specified down to individual gates. And it does the job. So you see how simple it is. I mean, the fonts are pretty large right now, but this is the 100% font level. This is what it looks like in reality. And you see it's like 1, 2, 3, 4, 5 pages, including all the commentary. You know, there's a lot of commentary everywhere. So pretty straightforward. Cavia as well, much shorter. Cavia is shorter than this. So now you know exactly from the gate level up how to build a colorful VGA video circuit based on video memory mapped video, and memory mapped character definitions. I hope you've enjoyed this. Next episode will be about the computer proper, which is probably more interesting for a lot of people. But it's important to know how to generate a video signal, and now you know it. So I hope it's been useful to you, and I will see you next time. Thanks for watching.